시작해도 괜찮을까요? 네. I think it's time, so let's start this seminar. The speaker is Chul Kim from Seoultech. He'll talk about large logarithm resummation in exclusive processes. Please start when you're ready.
Thank you for the invitation. Today, I'll talk about the large logarithm resummation in exclusive process. So, okay. So basically, exclusive process is unlike inclusive process. Exclusive process is very sensitive to some infrared physics. So basically, the property is somewhat very different from the inclusive process. So also, it will be difficult to handle that kind of infrared divergence and actually the size of the inclusive process. Today, we consider how to consider exclusive processes consistently and systematically, considering the resummation of the large logarithm and so on. Okay, so to begin with, let's consider inclusive process here. For example, here I have considered the E plus E minus annihilation, and here is QQ pair production. Actually, when you consider this kind of inclusive process, actually at reading order, it can be simply given by, and at next reading order in alpha s, actually we have to compute that kind of virtual contribution and the real glue emission from the here glue can be emitted from the QQ pair like that. Then actually, after the computation of the next reading order, we can obtain the following result. Here, sigma zero is the tree-level scattering cross-section. Bone-level scattering cross-section is given by like that. And the next reading order corrections is finally can be given as 3/4 times alpha CF over pi, something like that. So basically, if we consider this virtual contribution only, actually this virtual contribution can involve some infrared divergence. Also, these real glue emissions can have influence collinear divergence when collinear the glue can emit parallel with the curve. And also, as when the emitted gluon's energy is small, actually, so we can face soft divergence. That kind of collinear and soft divergence can cancel if we combining these virtual contributions. Actually, this is well known. This is well known as Kinoshita-Lee, Dow-Berg, KLN theorem, like that. Also, at higher energy scale, actually, this next reading order correction can be considered to be too small because alpha coupling just follows the asymptotic freedom, right? So, so actually, at high energy scale, these one corrections can be negligible, right? And this path, the reading order contribution is dominant at higher scale, maybe give some impression that actual this tree-level configuration seems to give a dominant contributions, right? Because a high order correction can be negligible. But actually, this impression as this naive speculation, I mean, maybe reading order actual tree-level configuration seems to give a dominant contributions, not exact. For example, we can consider the contract. We can consider also from the E plus E minus annihilations. We can consider the exclusive direct cross section. Actually, 1978, the Sterman and Weinberger, they have first successfully they have to calculate this direct cross section to next reading order. Actually, yes, it is called Stelmer-Weinberg jet. Actually, for this, actually, from the E plus E minus annihilations, basically, so we consider the QQ bar pair production. Actually, because of the large energy of the annihilation energy, actually, this produces the QQ bar pair as very energetic, as also as moving to back direction, right? So actually, then maybe that is we can consider the gluon emissions. So actually here, when gluon can be emitted outside of the R is the angle between the gluon and the produced curve or anti-curve. So the opening angle is if opening angle is larger than R, actually we can just drop that kind of event, and we only keep when gluon can be emitted collinear to the produced curve and the anti-curve like that. Also, we have to include this kind of soft gluon energy, soft gluon emissions when the energy is smaller than beta times over Q. Here is beta is just a parameter, small parameter. Actually, it should be less than 1. Maybe, for example, beta is just around 0.1 or 0.2, like that. Then, just by including these soft gluon emissions, we can remove soft divergence, right? Also, just as including this collinear gluon radiations within the size of R, then we can also overcome the collinear divergence. So the result can be given to be infrared finite, and then we can calculate. Actually, this is, I guess, this would be actually the first calculation about the jet, and next reading order. And then we can successfully obtain that kind of result. Actually, this F2 is for standard Stelmer-Weinberg jet. Actually, is given as the this digest scattering cross section over inclusive total scattering cross section for QQ bar. And the result should depend on the jet parameter beta and R. So we obtained that result. Actually, this calculation is actual calculation, so there is no scale dependence here. But instead of that, actually we have some large rho. For example, is beta and R. If R or is beta would be small, actually, so we can pass the large rho. Actually, maybe as the calculation would be considered to be perturbative. So 3 jet contributions can be simply given by just subtracting the dijet ratio from 1. Okay. So actually, from these calculations, for example, if the jet parameters are given to be very small, for example, as beta and R is much smaller than 1, actually, the digest configurations looks very similar with the tree-level configurations. Actually, this special jet is just looks like just a Cog and anti-Cog, right? And also, so we have a very small. Actually, we have a soft glow radiation, but this soft glow energy is to be very small, actually. So if beta and R is given to be very small, like that, actually this digest configuration just looks like the tree-level configuration, something like that. So naively, we can guess that actually this tree-level configuration would give us the almost the leading order, would give the almost the same result as the leading order result. We can ask that like that. But however, the digest cross section with this small parameter beta and R gives the much smaller result than the leading one cross section, right? if we consider the ratio 1 over sigma here, sigma is one level cross section, and this is the Stellman-Weinberg jet scattering cross section, direct cross section. For beta is 0.2 and R equal to 0.4. Actually, the result is 0.86. However, if beta is 0.1 and R is 0.2, actually this result is the direct cross section is just as helpful over the leading of the cross section. Right. Also, if beta is 0.1 and R 0.1 is just as 40% of the reading of the result. So even this situation looks like the three-level configurations, right? It's very similar with the three-level configuration, even though very similar with the configuration, actual result should be very different, right? Okay. So basically, if we have this small parameter, for example, beta is 0.1 and R is less than the 0.2 or 0.1, something like that, this small parameter gives the large rho, right? Actually, then we have large rho. So as even this is one correction. So as is suppressed by alpha s at high energy, actually we have large rho like that, multiply the large rho. So the perturbative expansion doesn't work well. So basically, yes, we have to resolve that kind of large rho contributions to all order in alpha s. So in order to resolve that kind of large logarithm systematically, we need to separate the QCD interactions into multiple contributions with various scale. Actually, as we require QCD factorization. Okay. So now we consider the factorization of the diagonal cross section for the Stellman-Weinberg jet. Actually, at the end of the day, we can realize this diagonal scattering cross section can be factorized into the hard, collinear, and the soft and the collinear soft contributions. Actually, divided into the four factorized function, something like that. Here, schematically, as I showed how the full QCD interactions can be factorized into the hard and collinear and the soft and the collinear soft, right there. Okay, so basically we have a hard energy Q. Actually, the E plus E minus actually the central mass energy is just as given as Q. Q is large energy like the G boson or Higgs boson, something like that. Mass. And so basically, we can enumerate out these harder interactions. But for digest productions, actually, these harder interactions only just reside in this virtual as of these virtual contributions. And also, as we have two back-to-back jet, actually, this is the produced curve and anti-curve just moves very energetic. Actually, it can form the jet. So we just as set one direction is n direction. N is right vector, and the opposite direction is just called as n bar direction, something like that. So as Q2 bar pair, actually each curve can form this jet. Actually, this jet is basically described by collinear interactions. Actually, these collinear interactions for n directions. Actually, here is m bar p is the dominant energy content dominant moment component of the n collinear particle, and the p pub is transverse momentum, and the n p is just the smallest. For m bar directions, actually, n p should be dominant, and the p pub is next, and the m bar p is the smallest component, something like that. So for n collinear particles, actually, this size should be Q times, EJ times R, something like that. Actually, EJ is given by Q over 2, right? Each jet has the energy EJ So it's 2 times of EJ should be the same as Q. So, the anchor momentum can be power counted as the largest component is Q and second largest component hep-ph is Q times R and Q times R square. And the auxiliary is given by P square is Q square times R square. Okay. Also, as amber collinear has the same property. So each auxiliary is given as Q square times R square, something like that. And also, we have to describe this jet veto path, something like that, right? So here is soft gluon emissions with the energy less than beta times zero. Q should be included this jet cross section. So, in order to describe this jet veto part, we have to introduce the soft mode. Soft mode is Q times beta is a typical energy of the soft gluon, and the momentum can be power counted as, and the auxiliary is given as Q square times beta square. And finally, also we need one additional degree of freedom, actually two. For n collinear part, actually we can imagine collinear soft mode, something like that. Actually, this collinear soft mode is relevant to also its JP2. So basically, this so it's just as this is just collinear and soft. So basically collinear and soft, right? So so if this energy, if this moment, this degree of freedom's energy is smaller than the beta times zero, and Q, this emission can be invariant. Also, even though the energy of this gluon is larger than JP2, but if it is collinear, I mean, if it just radiate within the size R, the radius R, it can be included. So as we have to include this, we have to also consider this collinear soft mode, and also as amber directions, we have also this collinear soft. This collinear soft mode has the smallest auxiliaries like that, Q square times beta square times R square, something like that. Maybe it's looks complicated. So anyhow, so finally, including the whole degree of freedoms, I mean, as hard collinear and soft and collinear soft part. And then finally, this digest scattering cross section can be factorized as the, I mean, as hard part and soft part, described the JP2, and collinear part, n direction collinear part, n bar direction collinear part. Finally, we have the n collinear soft, I mean, C soft, collinear soft. In other words, yes, C soft contributions. Like that. So, n bar directions collinear soft. Also, so each factorized functions can be calculated as at the to the next reading order in alpha s, like that. This is hard. Actually, this hard mode actually is for this hard mode is we have that kind of large log. Actually, the large log has the form log mu square or q square like that. And the typical size of the collinear part would be mu would be e square times r squared, something like that. And the soft mode actually 4 times beta square times q squares. Actually, this is correspond to the typical auxiliaries. As I just described the previous page, like that. Actually, collinear part as auxiliaries is given by q square times r square, something like that. Soft part q square times beta squares, and collinear soft part is Q square times beta square times R square, something like that. Also, in the logarithm, in the argument of the logarithm, actually that kind of series can be included.
What is EJ?
Yeah. What?
What is EJ?
EJ is jet energy.
Okay.
Jet energy is given by over Q over 2 in this case. Okay. Then, okay, so now yes, we have that kind of QC factorization. And then, using this factorization, we have to actually sum the large rule. Basically, so in order to resolve the large logarithm, actually, we can employ the normalization group evolution like that, you know. Okay, let me show the idea briefly. Actually, this factorization can be done at arbitrary scale mu. So let's call it a factorized scale mu, something like that. So at any arbitrary scale mu, we can factorize that kind of stuff, right? I mean, at the end of the day, this scale dependence should cancel if we just combine the whole bunch of the this factorized function, right? Anyhow, so at any arbitrary factorized scale UF, we just factorize the this digest scattering cross section into the sixth part, like that. Then, as you know, for example, if UF is much, for example, if UF is much smaller than Q, actually this hard functions involves a large rho, right? Large rho, that should be resolved, something like that. So, so generally, we just as consider some hard scale. Hard scale is given to be just around over Q, something like that. So actually, basically, so to begin with, we just let's calculate this hard function around the hard scale. At the hard scale around the Q, then we can at hard scale actually so we don't have large logarithm anymore. Then we can evolve this mu dependence. I mean, so using the renormalized group equations, we can evolve this hard function to the factorial scale. So while doing the evolution, that kind of evolution, we can automatically resum that kind of large rule systematically. Also, collinear part actually is n and n bar direction should be the same. So for this, actually, we can set the typical collinear scale, the characteristic collinear scale as u is equal to EJ times R, actually. Then basically, as we can, so for that choice, actually, we don't have any logarithm. So starting from that scale, if we evolve the any arbitrary factorized scale, we can systematically resum large rule like that. So so as a hard scale, so as at any arbitrary factorized scale to the factorized scale, actually from the hard scale and the collinear scale, soft scale, and from shear soft scales, after the evolutions, we finally can resum the large logarithm to order in alpha-s systematically. So as here, as I just briefly showed the resummed result like that. Actually, the resummed result becomes worse. What I mean here, the resummed result is given to be much smaller than the leading order result, much smaller than the fixed order result. I showed previously, like that. Okay. Actually, the resummation gives the larger resummations. Actually, gives more suppression. Actually, for 0.2 and R 0.4, 0.8 around. And previously, I mean, if we just consider the fixed next leading order calculations, actually that result is around 0.5, now it's 0.4, something like that. And basically, at the fixed order result, previously, I mean, it's just around 0.4, now it's 0.25, something like that. So, listen to the result gives more suppression like that. Okay. So, exclusive process actually, even as that kind of configurations, just as looks like very similar with the three-level process. Actually, the result is very different. Actually, the result is much smaller than the leading order result, simply. So actually, so we may have to consider what happened, right? So I think basically, if we consider the particle production from the E plus E minus annihilation, from the cubic pair production, based on the gauge series picture, actually the natural description is just as looks like that. I mean, basically, this produced a very energetic quark and anti-quark. Actually, so, around there, actually we have collinear, enormous collinear and soft gluon radiation, something like that. This is basic picture of the gauge theory. Then actually, if we when you consider the exclusive direct cross section like that, right? Or that actually is that kind of exclusive I mean so that kind of just that kind of phase space constraint severely restricted this collinear and soft gluon radiations, right? So and as a result, the exclusive result, I mean exclusive dielectric cross section in the previous page should be severely suppressed compared with the leading one result. And now let's turn to exclusive heavy cup dielectric cross section. Actually, so previously, as we just mentioned the exclusive dielectric projection, basically the jet initiating parton should be has been regarded as the massless fermion. From now, we will consider the heavy cup pair production from E plus E minus annihilations. So as this each heavy core can initiate the jet. So in this case, the factorization was basically this study can be analyzed and factorized very similarly with the massless case, basically. But we have to modify the collinear and the C-soft sector to include the heavy mass like that. So what I'm saying here is actually previously we just factorized the exclusive dielectric cross section and hard and soft and collinear sector. Collinear sector can be divided into the collinear and the collinear soft. Also as an ambiguation, we have the same stuff. So this collinear sector can be modified to include the heavy mass like that, right? Here, the heavy mass is considered to be much smaller than the center mass energy of the electron and the positron, right? But so this heavy curve is just boosted, okay? So it's basically this heavy curve centers can be considered in the collinear sector and the collinear soft sector, right? So the calculation is even as so when you include the heavy mass, the calculation become much more complicated. But at the end of the day, as I just completed that, I'll just and here is B. The parameter B is given as M squared over E squared times R squared. something like that. And the B, here the B is square root E square times R square plus M square. So if we consider the method sweeping, B goes to 0, and the B is just end up EJ times R, right? For this method case. And the collinear soft sector actually can be obtained, that's reasonable result can be obtained like that. Actually, it looks much more complicated than the previous case. I mean, message case. Anyhow, basically, as in order to obtain this collinear soft sector, actually, we have to apply the effective shear, what additional effective shear? I mean, the boosted version of the Hepburn effective shear. You know, yes, Hepburn effective shear. Basically, inheriting out the degree of freedom with the obsolete m, whereas p scale equal to m scale, like that. Then we have some kind of residual interaction at low energy, right? So boosted case can be, boosted case also can be applied to the also to the this boost case, this boosted cases actually the same, the boosted version of the Hepburn effective shear can be applied, and after integrating, just integrating out the degree of freedom, p scale is m scale, and like that, and then we can obtain this this collinear function. Then using the boosted version of the Hepburn effective shear. I mean, yes, employing just considering the residual degree of freedom, we can compute this collinear soft function like that. So calculation, even calculation seems more complicated. Actually, if we just take a limit m goes to 0 or p goes to 0 in these calculations, we can obtain the same result in the Bessel's case. Okay, so this calculation looks consistent. Okay. So now we have considered the factorization of the for the exclusive helicopter cross section like that. So actually, so we can take the same straightest for resumming large logarithm. So actually, so to the arbitrary factorized scale from hard scale and collinear scale and soft and collinear soft scale, just as during the RG evolution, we can systematically resum the large log. Here, B is has been the collinear scale has been modified to square root E scale times R scale plus M scale, include the heavy mass, right? And also, collinear soft scale is given by 2 times beta and B, the typical collinear soft scale. Okay. So, during that kind of RG evolution, actually, we can obtain this exponential part. In this exponential part, the large log has been automatically resummed. Also, the remaining factorial function are considered to have no large log because this hard function, the hard function at scale, hard scale Q, actually this log can be suppressed, right? Also, as we can see other factorial function like that. Okay. This exponential part is given by at the end of the calculation and the end of the calculations, we obtained this exponentiation part like that. Here is S gamma is Sudakov factor. Actually, it is defined as this integral form. Also, A gamma is like that. Here is B is the QC beta function. You know, d alpha over d log mu. Actually, it can be expanded like that. And gamma C is well known cos of anomalous dimensions. Okay. So as you see, actually, this S gamma includes the double log. Okay. What I'm saying is here is actually, you know, For example, the collinear part and collinear soft part include the deckage of double log. This double log, right? And also as we have single log. So what I'm saying is here, actually, even as we have just as first order in alpha s, the factorized function also as the whole scattering cross section actually involves the like the area is just a schematic of the right row. Okay, and alpha s times l. So because as this is large row, so it's even if alpha s is small, alpha s times l, this combination is not considered to be small. Okay. Also, it's much more large. It's much larger than this quantity, right? So if we just list some that kind of stuff, with just as unknown coefficient, actually this is called leading log resummation. Also, as including this single log, I mean, this is next to the okay. So this exponentiation pattern actually is the result of the resummation to the accuracy of the next region, including the single alpha times. Just as well as alpha times L scale and the alpha times L. Okay. So as this Sudakov law includes the resummation of the that kind of stuff to all order in alpha s like that. And this is the result of the single law. I mean, it's the next leading law, alpha s times L, something like that. This is large law, and something like that. Okay. Then this result actually here is I just show the service numerical result. Actually, in the diagram, in the plot A and B, actually I have I made a plot. Actually, this is just next to leading log plus next to leading order contribution. I mean, yes, this is the sum the result. And this red line is just piston next to leading order result. Also, as we have the black dashed line is next to leading order, but as in this case, as we just ignore the helical mass, just as take regarding the helical is just a massless fermion, and this red dashed line is fixed next to leading order for massless case, right there. Okay. So it's here is I just as consider this E plus E minus annihilation at G4 and for plot A as beta is I mean this Z2 parameter beta is given to be 0.1, something like that. Just betting the size of the R, I just checked that. So as you see, this helical, I mean the helical digit cross section, just as including to include the helical mass, actually very stable, even R goes to 0, right? But for Messer's case, actually, Messer's case is as R goes to 0, actually, as we this scattering cross section should be collinear divergent. Actually, as we basically as we have a lot of fluctuation here, right? So it's so for this region, R goes to 0. For Messer's case, as we cannot rely on that result. Actually, it experiences a lot of fluctuations like that. Also, as just as spanning the Z2 parameters, we have also considered the same plot, right? It's just the setting as I is 0.4, something like that. Also, as below, here is at also as G4, with the beta is given to be 0.1. Actually, as we just as consider the variation. We just as consider some kind of uncertainty of the resummed result for the heavy curve direct cross section. Here, red line is just a fixed depth reading of the result. And after the resummations, we basically the central value is the default value of the resummed result. And this gradient is uncertainty for the that kind of resummation. Right? So even as including the uncertainty, actually, we just clearly see the result result actually would give us the smaller result for the compared to the just naively obtained next to reading of the pistol calculation. Also as here, just as spanning Q, actually as we just consider the helical digest skeleton cross section. Okay, here. Just if we consider among helical digest cross section, if we consider the BB bar pair, I mean B digest cross section, the ratio with B is 0.1 at G4. Actually, when it's compared to the massless case, actually the result, the helical result is increases by almost over 10%. With a variation of R from 0.2 and 0.4. So what I'm saying is here is actually this mass correction gives the significant corrections to the massless case. Right? Also, so when you consider the charm, actually the enhancement is somewhat small, but still is given by around 5%, something like that.
The reason or simple reason why you have a more increase.
Basically,
So Biko case is B digest is increased relative to massless core case.
yeah.
So simple reason.
Actually, the page space just has become just broader, basically. So when you have usually when you have a massive fermion, actually the
Phase space is just smaller, and also radiation is just smaller, naively, right?
yeah, but usually, yeah, for a special case, actually the typically as collinear size is just as becomes broader due to the presence of the heavy mass. Basically. Okay, so yeah. So Horace collinear calculations actually compared with the massless case, actually the massive case always gives the larger result. Basically. Okay. Maybe it will be helpful for your question. So, and then, actually, as previously, as we have considered the exclusive heavy cup digest scattering cross section, right? And now we can consider the exclusive heavy cup pair productions, just taking R, taking the limit R goes to 0. Actually, even as we consider the limit R goes to 0, actually the digest scattering cross section collinear safe, I mean, it's IR safe, right? The reason is because of the helicon mass, actually, in this case, there should be no collinear divergence. So it's without setting the jet, I mean, it's just as considering the limit equal to 0, actually, we can compute the exclusive helical pair production right there. So as you see, this diagram, this is just a hemisphere. So actually here is from the E plus E minus relations, actually this energetic heavy core actually basically can be produced back to back, right? So as in this case, is we just as include the energy core. So it's actually include some soft glow radiation with energy is less than beta times Q. Then as with because of this inclusion of the soft gluons, we can remove the soft divergence. Also, and here is we just as drop the whole event, I mean, as collinear balloon radiation from the core, right? Only just as energetic core, just as core pair is produced in this case. So, in other words, it can be just as it can be considered as hemisphere isolation, right? So actually, it's you know, yes, for example, it's photon isolation, right? So photon, in case of photon isolation, actually, it's for the energy photon, and around the cone, setting the cone, and around the photon, and so we just as remove the whole hadron productions, energy hadron productions, just keeping the just hadrons with soft energy. So it's like that. Actually, around the heavy core, actually there should be no energetic hadron and gluon radiation here, and only the soft gluon radiation just can be included, something like that. So finally, yes, actually this veto so cannot be measured. Actually, I mean, as in the final state, actually we just as can observe. In this case, we just as can observe heavy cup top pair, heavy cup pair, something like that. Yeah, like a top pair. So setting R, so it's taking the limit I go to 0. Actually, taking the limit I go to 0, we can obtain this collinear function and the collinear soft function like that, right? So, I mean, as in the previous result, from there, just taking the limit I go to 0, we can obtain this result, and in the same way as we can obtain this collinear soft part right there. Then using this factorization theorem, we can consider the exclusive heavy cup production, and also as we sum the large row here. Actually, so we have the large row of the heavy cup mass. Okay. Here, in this place, I have considered the exclusive BB bar pair productions like that. Here, this is BB bar pair exclusive BB bar pair production. Actually, this is resummed result, and this is fixed order result. Actually, resummed result gives more separation like that. And also, as we here, as we compare the digest cross section, I mean, as with R is 0.1. R is 0.1. Actually, gives the more page space, right? Slightly more. So actually the result is somebody else. Actually the difference is just like that. Also, so when R is given to be given as 0.4, actually we have some kind of somewhat large discrepancy from there. Okay. Also, so in the below here is we consider the exclusive top pair productions. Actually, here is veto has been set 0.1 energy cut is just sparing the just the center of mass energy. We have considered the top pair. Here, actually the calculation is very interesting. I mean, as F2 is just the exclusive top pair, the ratio of the exclusive top pair over the total cross section, right? I mean, it's T by X. So in this case, actually almost just 1. So it's never I mean, it's a pixel calculation, and the result calculation is just as also gives just a small expression compared to the leading order or total inclusive cross section. And as Q becomes larger, actually the cross section exclusive top pair production gives us some separation, but still has almost 80% or 70%. of the leading order or total inclusive result, right? So what I'm saying here is in case of top, actually it doesn't experience large suppression, even as it is exclusive, right? The reason is actually as a dead cone effect actually answered the reason. Basically, if we consider dead cone effect, actually dead cone effect restricted the collinear glow radiations. I mean, so with a very narrow angle relative to the energetic heavy core. Okay, so this is would be a basic picture. So this is not much different than the this exclusive case. I mean, as original basic picture, basic configuration, or as basic picture is not much different than this exclusive case. Okay, so it doesn't give us the separation much. Okay, so far we have considered the exclusive heavy dielectric cross section and the exclusive heavy production like that. So from now as we will consider some application of it to the quid process like that. Here is I just wrote the paper with the Lin, Dai, and Adam Libovici, and about the lepton universality violation. So I have said my title is my paper's title is Universal Lepton Universality Violation in Exclusive Process. Actually, without introducing the Newpill's model, I just realized that we can see a lot of large lepton universality violation in exclusive process. Okay, to begin with, let's consider the exclusive G decay, So basically, if we consider the inclusive G decay, I mean as a G decay to lepton pair, I mean as including the any particle, basically as photon, something like that. Actually, this ratio, I mean as L1 and L2 is different lepton flavor. So as in this case, this ratio, I mean as for different lepton flavor, actually gives just a small difference. Actually, almost identical for its inclusive process, right? However, in exclusive G decay, for example, just as if we consider just a G decay to lepton pair, also as for the emitted photon radiations, we will give severe constraint on this photon radiation. In this case, basically, rather large difference can be expected due to the IR sensitivity of this exclusive process. Actually, you can imagine the you can imagine some discussion in the previous pages. Also, basically, as for this exclusive G process, for infrared finite result, we need to take a small photon energy cut, E cut, like exclusive heavy pair production, which is also basically even as experimental guys has not assigned the E cut definitely. Actually, E cut can be deduced from the for example energy resolution of the detector, something like that, right? Actually, this E cut, so as below, I mean, so when porous photon emissions below the E cut, actually we basically we can include that kind of stuff, right? So actually, this E cut can regularize some soft type, regularize the soft diamonds, right? Also, we can guess the porous Mercedes pattern, I mean, Mercedes fermion productions. We can consider collinear divergence. But here, actually, for this QED process, we will include the lepton pair mass explicitly. So collinear divergence in mass's case can be converted as the large log of the lepton mass, right? In this case. So our point is like that. So it's even we so as for example, as if we consider the lepton vibration between the electron pair and the muon pair, actually we just as point out that actually muon mass is much larger than the electron mass consideration, right? Basically, muon mass and electron mass is much smaller than, for example, for SPDK, for SB measurement mass, like that, or G boson mass, right? So for inclusive case, actually this small lepton mass, even between the electron and the muon, the mass gap would be large. Actually, in inclusive process for heavy particle decays, actually, so this difference can be ignored. However, exclusive case gives a very different situation. Okay, in this case, I mean, as exclusive case, actually large difference between the muon and the electron, large mass difference gives a plays a significant role for the lepton violation. So here, this QD process is similarly, I mean, GDK to, I mean, here is I just consider the exclusive GDK, G2 lepton pair, and with setting the energy curve like that. So is here the pitot parameter beta is much smaller than 1. For example, is this is 0.1. This case, actually, the factorization theorem is very similarly given right? Is given to be very similar with the case exclusive heavy pair production. Okay, hard and soft, and also M collinear sector and M bar collinear sector. We have a collinear, and this B represents the collinear soft part. Here is yeah, B represents the collinear soft part, like that. So this hard function is relevant to the hard scale. I mean, as Q. Q is the mg in this case for GTKs, and the cut is very small, and m is the lepton mass, and beta times m is collinear soft scale is much smaller than, but still it carries lepton mass. Okay. Just as converting the QCD calculations to the QD calculation. Just as we obtain the higher order result, let's read the result for the hard function and soft function for this energy cut, relevant to energy cut and collinear soft functions. Right. Also, we can take the same. We can take on the same strategy for resolving the large log here, but now. Rather than the calculating the this decay rate exactly, here is we consider the ratio for each different lepton plate for each different lepton pair production of your different lepton flavor, like that. So here, when you consider the range, actually we can immediately realize that the hard part and the soft part is given to be the same. As far as energy cut is given to be the same for each case. So in this case, as hard part and the soft part, I mean here, the among the factorized function, the hard part and soft part, actually is not as related to the lepton mass, so it can be safely cancelled. Then the remaining part in the ratio should be C and B, the combination of C and B, right? But actually, actually this ratio involves the large log. So large log still remains due to the large mass difference between the different leptons, like that. So actually, the exact calculation for the exponentiation factor for this large rho is just given by like that, you know. But if we just ignore the scale variation of the coupling constant alpha, and then I'm just speaking the alpha as constant, and then yes, this large exponential factor can be simplified. Actually, like that. The structure like that. Actually, this is double log. Actually, one large log is it just comes from the large mass difference. And also this is energy cut. Also depends on the energy cut. That gives the large log. Also this is cost of one loss dimension, and single log also is depends on the large mass gap between the different vector. Okay. So here is plot A just as represent the just bearing the energy curve from 0 to 2 GB for GDK. We just as the delta. Delta is the remnant. Delta is R minus 1. Right? So it's lepton flavor vibration. The lepton universe vibration just as bracket looks like that. Here the red dashed line is just a pixel result, and this result is just a leading order result. Resum the result. Large log resum the result. This is next leading order pixel next leading order result. And as we see, actually Fourier's tau mu between the tau lepton and the muon, actually we have 5% of the difference violation in the scale ratio of the decay rate. Also, between the muon and the electron, actually we can imagine the almost larger than the almost over the 10% difference from here, from the standard model. Okay. Also, as tau E, we much bigger result, something like that. So yeah.
So please keep going.
Okay.
Say whatever you.
Okay. So yes, roughly here is so we read as E cut is given at E cut setting the E cut as 1 GB actually is the violation result is 0.5% for tau between the tau and the mu, and the muon and the electron, and 10% and 17% between the tau and the electron. Okay, so it's interestingly, the same analysis can be done, can be performed in the exclusive J-psi decay. Actually, for a spectral version, actually, we can consider the same impact. Maybe the size would be somewhat small because mg here is can be replaced with the J-psi mass, but we can still observe the sizable effect for the lepton violation.
So question.
Yeah.
So first of all, you showed this resum result in the middle,
Yeah.
just above the plot. You have analytic form for R1 to G.
Yeah.
So
yeah.
there I can see directly the M1, M2 dependence.
Yeah.
But can I infer this MG dependence? For example,
MG?
the case of G boson decay and J psi decay, the mass initial mass is different. So this mass dependence appear. Where does it appear in the gamma C?
You just as you are just asking is why is
mass of mother particle? Where does it show up?
yeah, basically mass of the mother particle is not relevant to that. Actually here the alpha the scale can be I mean scale mg can be involved in the scale variance in the coupling constant alpha, but actually for as large rho, yes, there would be nothing. What I'm saying is here is actually the hard part can exactly cancel between the product, right, and the soft part. So this is if we just as apply this factorized theorem, actually definite mg dependence would be gone. Actually cancels in the cancellation of the hard part.
So I think another question is that
Yeah.
this result looks very interesting and surprising.
Yeah.
I think more than 99% of the people will calculate just three-level G2 L plus L minus vortex. It's just a three-level calculation, which is just almost one, right?
Yeah.
But now you show that the degree of lepton flavor violation
Yeah.
purely in the standard model you still can be as large
Yeah,
as
just
1%.
around 10% is like that. Yeah.
So do you have I guess, is it consistent with the data?
I don't know. Actually, it has not been observed,
It's not?
measured. Actually,
But
people just consider the inclusive case. Actually, for the exclusive case, actually, so many exclusive process has been measured. I mean, it's about the BT case, right?
But I think there is a very clear, good clean data for G2 E plus E minus G2 U plus mu.
Yeah, I think so. But still, yeah, as far as I know, it has not been measured clearly. Actually, some data just include progress electron pair and the photon, and
So
yeah,
there is
in the particle data.
E plus E minus it includes some
Yeah.
implicitly some photons, right?
Even as exclusive, yeah, there would be a few just as experiment data about the exclusive, for example, muon pair plus photon. I mean, it's hard photon, something like that. Yeah, I think it's so. Yeah, this result is just as surprising. So yeah, basically, I just so when I obtained this result I just submitted this draft to the PRL. I don't know why PRL is didn't accepted my paper. Actually, they just suggested to publish in PRD. So anyhow, the result is just as surprising. Interesting.
But wasn't there any referee report about this? I mean, comparison with the.
Actually, they can't. Actually, it's basically as referee just at the first stage of the just communications, referee just as argued that my paper is somehow incomplete, but the reason is not clear. Actually, so nobody, I mean, no referee, actually several referees, they just responded, but their answer is not clear. Actually, we just as reported every question about from the referee. And then finally, it's just one referee just suggested that to publish the paper in PRD. Just so. Okay, so actually, we can also apply the result to the exclusion BT case. Actually, maybe the interesting stuff is something like that. The SD2 muon pair and the electron pair. But actually, because this is Sudakov version, so actually, for this process, it will be somewhat difficult to apply our result directly. The reason is actually this is a power suppressed process. actually. So higher twist component would be important. So the calculations would be somewhat would be more messy. So instead of that, we just applied the our result to the B2 L and neutrino, and also as KO to lepton and neutrino. So in this case, actually, we have only one sector for the collinear and the collinear soft part. So the calculation is actually, so when you consider the ratio, so so rather than considering the scale, actually just the C times B, the ratio of the just the single C times over B. So considering the ratio of the single B, C times B, we can consider this difference. Actually, also that should be actually this branch fraction should be should depend on the lepton mass like that. Actually, and the B major mass something like that. So yes, just as keeping the this factor actually, and then removing then we here is we consider the this plane violation like that. We define the plane violation in this case like that. Then we can compute the this considering the larger resummation, and actually also the result is just yeah around just less than 10%, but it's more than 5% like that. Yeah. Also, as muon decay width to be less than the electron, something like that. Also, as for KO, actually the result is so it's just as betting the just as choice with the choice of the different energy part, we obtained that result. And for this KO, something like that. Okay. Now this is not surprising. So also as finally as we just as consider the as you see, actually as here this result result although as this result result is here as we just as consider the ideal case actually, right? So as there should be no collinear photon radiation here, but you know, but it's realistically basically when photon is emitted from the energetic electron. Basically, in the detectors, it is very difficult to separate. I mean, to distinguish photon and the electron signal, right? But contrary to the case of the electron, actually, is muon for muon actually is rather as somewhat as easy. So just as considering that kind of situations, actually. When you consider the ratio, for muon, we just remove the whole collinear photon radiation. For Y, we just kept the collinear photon radiation from the electron, setting the jet size of R is equal to 0.1. Right? So basically, the photon. So basically, the electron decay width become larger in this case because as we include the more page space, just a setting this case, then decay width for electron becomes enhanced, significantly enhanced. Actually remove the gap between the when you consider the when you imagine the ideal case. What I'm saying here is actually when we consider the decay width for photon with the for electron with the jet size of R 0.1, actually we would have the same result for the muon. Yeah, here is when you consider the ratio as for muon, we just as remove the actually we just remove the whole collinear radiation from the muon. So muon is the So when we just as modify the electrode process compared to that case. So, so we can conclude that actually the violation, random flavor violation for its exclusive process can be significantly changed by experimental environment, right? Actually, I think the experimental environment is not simple. Is maybe more complicated, right? Like that, the isolation of the electron in the final state, right? So if we just include some photon around the electrode, then signal can be significantly changed, right? So recently, LHCb just has found that they just has reported large electron universality, right? But here is surprisingly, actually electron signal looks much larger than the muon signal. It's somehow as, at least to me, it's somehow as questionable. But yes, I just guessed that actually at the LHCb, actually they just used the very boosted B measure and decay to lepton and try to separate the photon, collinear photon from that signal. So maybe maybe as that case, maybe I guess as there could be a lot of uncertainty in that kind of experimental environment. So finally, yes, let me summarize. So unlike inclusive processes, the exclusive process are infrared sensitive. So in order to overcome, we can introduce a few small parameter, but that result in the large rho to be resum, or in hep-ph or alpha coupling constant. By choosing the parameter to be small, we can consider exclusive process, of which configuration is very similar with three-level process. But, as we observed, the large rho of the small parameter makes the result much smaller than the leading order result, right? So this is a typical, typical stuff for exclusive process. For massive perturbative, we can describe the exclusive process without collinear divergence, as we observed, but the large logarithm of the mass gives the large deviation from the leading order result. Yeah. Also, we can see the origin of the lepton universality violation. Okay, thank you.
Thank you very much for the nice talk. Any question?
Do you have any idea that what you are talking about today has any relevance to the calculation of muon G minus 2?
Muon G minus 2? Muon G minus 2, I'm not sure. Actually, it's for muon G minus. Yeah, I'm not sure. Actually, the main uncertainty is some kind of root correction, right? Inside the, yeah.
I think the B meson anomaly, the lepton universality in the B meson decay looks disappearing.
Yeah.
And for the just the previous slide, you consider pure leptonic decay, but you can also consider B to D how new.
Yeah, I can do that.
Have you got that or not?
Maybe yes, I can do that, but in that case, actually, this is somewhat some kind of simplification. Actually, this is basically my calculation is based on the digest cross section, digest calculation. But actually, basically, I can do that, but but the space constraint is more complicated in case of B to D, because in this case, D would be also heavy, right? Also, as the mass effect of the D measure, yes, would be also as important. But even as with that, I can do that. Basically, I can do that, but yeah.
Are there still, I mean, there are some deviations.
don't know, it's maybe. And also, as recently, as you know, also now as that kind of physics is has been issued in the neutrino physics. Actually, in the neutrino for muon neutrino, and when they consider the conversion from the muon to electron neutrino, actually discrete process gives the important corrections. So neutrino community actually they're taking it serious.
So in the middle of April, do you know Alexander Tomalak?
I don't know.
I think he was a postdoc of Richard Hill.
Ah, yeah.
He will visit here a few days and give a
Ah,
seminar
really? Yeah,
on
interesting.
the proton size puzzle and radiative correction to neutrino physics.
Yeah.
Any other?
Actually, yeah, the Richard Hill's paper about the neutrino, actually, they actually almost have the same idea. But actually, I just reported uploaded this paper in the archive, and 2 years ago, actually almost the same time, 2 years ago. Maybe as a few months later, is actually Richard's paper has been appeared, but they didn't cite it.
Richard Hill.
Yeah,
Okay.
I don't know. I didn't. I have not communicated.
It's now less than secure again. Thank you very much.